Okay, so good morning, everyone.
Good morning, ma'am.
Morning. Okay. So I hope you guys have all tried to look at the assignment that was posted. So, any concerns or anything about the assignment?
Not so far, ma'am.
Okay. All right. So, yeah. So I would advise you guys to start a little early because there's also a programming component. So if you haven't started getting up to speed, I think this is a good time to just start off. Okay. Uh, yeah. So as was said earlier, like you can discuss among yourself all the assignments. I mean that's also part of your learning. But whatever you submit has to be your own effort. Okay. So yeah, so copying or any kind of plagiarism will not, you'll be penalized for it. So yeah, just a heads up on that. Okay, so were there any questions from the last time or any concerns about the course itself? Any any thoughts or anything you want to convey? Is everything going fine, comfortable for all of you?
Yes, ma'am.
Okay, so Rohit is happy, I think. So, what about the others? I know you have some other courses also. You're all of you doing some other courses, but I hope the course load and those kind of things is comfortable. Maybe it's less also. I don't know, but yeah, I just want to ensure that you guys are not pressurized. So yeah, just let me know in case. Okay. All right. So let's just begin. I'll just share my screen. Okay, I think it should be visible now. Okay, so the screen is visible, right?
Yes, ma'am.
Okay. So just before we move on to a new topic, what I just wanted to say something to conclude our discussion last time. So we were looking at this application in linear regression or the least squares problem, right? So where the unconstrained optimization problem, this one shows up. So where you're given an A and you want to find an X such that this norm of AX minus B that is minimized, the square of the norm that is minimized. Okay, and we just a brief recap is what we did is we tried to expand this. We first assumed that the columns of A were independent and to avoid any kind of redundancy. And then we applied the first order necessary conditions. Okay, to specifically we tried to find an X star such that the gradient is zero. Okay, so that gave us some expression like this. And we saw that A transpose A, this is invertible. And then we were trying to compute X star. Okay, so I hope by now you guys have tried to get comfortable with these kind of, expressions, right? So X transpose AX, so taking the derivative of these kind of expressions. So somebody asked me after the class about how they could compute this gradient. So just remember that this X transpose A transpose AX, so this is of the form something like this, right? X transpose QX. Okay, so this is actually where Q is a matrix, right? And this is something like Q ij xi xj. That's what this is going to evaluate to. Okay, so summation of all ij qij xi xj. So this is a polynomial, right, in x. And so now you know how to differentiate this. So that is a way you should get practice on taking the derivatives of these kind of expressions. Okay. Now, similarly, this one, so this is a vector. A transpose B is a vector. So this is going to be something of the form summation xi, some qi. Okay. So now you know how to take the derivative of the summation term, right? So with respect to x. So that's how you get practice with these. Okay. So now coming back, what we did is we found this x star. um as this expression. right? So this A transpose A inverse times A transpose B. So now this was a point for which gradient of fx star that was 0. So now at this point we don't know if this is a local optimum, I mean if it's a local minimum, maximum, or if it's a saddle point. There are various options, right? So the next step would be to verify that it's indeed a minimum point. So that's where we know a sufficiency condition, which is you take the second derivative or the Hessian. Okay, so this was the first derivative, the gradient. Now it's you take another derivative, another differential with respect to x. So that is going to give you just this part. Okay, so it's just going to give you 2A transpose A. Okay, so now if this matrix is positive definite, then you're sure that the x star thus computed is a local optimum. It's a local minimum, to be more precise. Okay, so is this really the case? Is it positive definite? To see that, you need to ensure, you need to verify if y transpose A is y, if this is greater than sorry, it should be greater than 0 for all y. Okay, so for all y not equal to 0, if you have this as true, then this matrix A transpose A is positive definite. Okay, so let us see if that's the case. So now yeah, you just take any y. Okay, so this is just about this y. Okay, so maybe just so that you don't get confused, I'll just change the notations here. So take any y, okay, and okay, let's just try this. So if you take any y, now if you say a, so this expression that you have here, it's just ay transpose ay, okay. So now this, recall that this is just the norm, okay. So this is just the norm of ay square, and this quantity is always going to be 0 whenever y is not 0, okay. So that's where you have that this is always going to be greater than 0. And so for this is true for every x. Any x you take, this the second derivative or Hessian is going to be positive definite. Okay, and so in particular, it's also true for the x star. And so that's where you can conclude that this point that you found here, that is a local minimum. Okay. One thing I want to also mention here is this is a very special kind of a function in which this A transpose A, okay, so this Hessian, this del square fx, this is going to be positive definite for any x. Okay, any x you take, you're going to get this as positive definite. So these are some special kind of functions. Okay, so these are called convex functions. We will look into them in more depth in a few classes down the line. So for these kind of problems, yeah, you already know for sure that the second derivative is going to be positive. The Hessian is going to be positive definite. So it's just enough to verify, I mean, to find a point for which the gradient is 0. Okay, so that's something to keep in mind. Okay, so any questions on this?
Ma'am, I couldn't recall. Was A having a full rank?
So A was, it's not a square matrix. So it's an m cross n matrix, but all the columns are independent.
Oh, so that's why we are saying that AY can never be zero. If what if Y is in null space of A? So
Yeah, there is no null space here, right?
okay.
Yeah. Okay, so yeah, so any other questions on this? It's been clear so far? All good? Anything, like you're all very quiet?
All good, ma'am.
All good? Okay. What about others? Sanila, is it okay?
Yes, ma'am. It's fine.
Okay. Tushar says it's okay. Shashwat, that's clear. Okay. All right. So do reach out if something is not clear. So now, whatever we discussed so far was for minimization problems. Okay, when we wanted to find local minimum. Now, even for finding the maxima, it turns out that you can have, analogous conditions. So where a necessary condition is that the gradient is 0, okay, at the maxima, at the local maxima. Now the second order sufficiency condition, just instead of checking for positive definiteness of the matrix of the Hessian, you check for the other way, the negative definiteness of the matrix. Okay, and again, the second order necessary conditions just become this: is if x star is optimal, then you have the gradient is 0 and the Hessian is negative semi-definite. Okay, so it's just a symmetric conditions that you have here. So you should verify, should go back and verify that you actually are able to prove these. So the proofs are almost identical to what we saw in class. So if you just work these out, and it will give you some more practice on these proofs, and you will ensure that you have understood the proofs. Okay, if you try to prove these conditions for the maximum. Okay, so so this is about the theory of what conditions need to be satisfied for the optima and how you can do some checks. So one thing here for the linear regression or the least squares problem is this inverse that comes in, this A transpose A inverse A transpose B. So here you have a closed form expression, but it turns out that many times computing the inverse is an expensive operation. Okay, so especially when you have this a large number of instances for examples, like in learning problems, you have a lot of data. So this matrix A itself is very huge. Okay, the M is very large. So computing this kind of an inverse is expensive for many cases. So we also want to see other methods to find the optimum. Now, these first order necessary sufficient conditions, even the second order conditions, in these cases that you saw here, you got closed form solutions. Okay, by closed form is you have this expression which you evaluate and just then you get x star. But it's not the case for every function. You may not be able to get a nice expression of this form. Okay, so that's why we need to go for some other methods, some other algorithms to solve, to find the local optimum. Okay, so that brings us to the topic of this class, which is on iterative optimization methods. Okay, so what we will do is we will just try to understand what happens in one dimension. Okay, because many times in one dimension the problem is simpler and you can at least visualize and get an idea about what's going on. Okay, so we will focus on those methods now, and some of these will also matter later on when you solve optimization problems in bigger dimensions. Sometimes you also make calls to these one-dimensional optimization methods. Okay, so let's start with these methods. So the first method we'll see is the bisection method. Okay, so suppose the function is continuous and differentiable. We are trying to find a point with the gradient 0. Okay, so that's what the local optimum condition tells you. So let's just see what we could do. So to start off, suppose somebody told you that this is a function you want to optimize. You want to find the minimum point of this function, and the minimum lies in some interval a0 b0. So x, so for some x in this range a0 b0, you are guaranteed to find a local optimum point. Okay, so then how would you go about? Now you have to do something to find the point at which the minimum occurs. So any thoughts on how you might do it? I mean, now remember, you can't exactly evaluate, like you can't find the x with gradient equal to 0, that you can't find the closed form expression, but you're allowed to, do some iterative methods, something you can keep trying. You can do one step, you can see if you have reached the point, and you can keep doing this. So do you have any thoughts on how you can now search for a point with gradient 0? Anyone?
We know the bisection method, sort of. So dividing the
Okay.
interval repeatedly.
Okay. Okay. So you have learned it already?
Mm, in a programming class, sort of. Yes, ma'am.
Okay. 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 So Rohit knows. What about the others? Have you seen the bisection method?
Yes, ma'am, we
Yes,
saw it in
Sumit.
numerical course.
Okay. Okay, you've all done it. So, okay, so this is something, then I'll just quickly go over this. So it's just that it's like a search method, right? So if you did a binary search in what you would have done in algorithms, so you kind of keep making the interval smaller and smaller. Okay, and that's the idea of this bisection method. Okay, so one thing here is that you assume that the derivative of f just changes the sign exactly once. Okay, so you can't have some function like this where the derivative changes signs multiple times. So here the gradient is negative, whereas here it's positive. So this is one change. Now here again there's a change, right? The gradient is, it's the slope is negative here. So these are two changes have occurred and this is not allowed. Okay. And also an assumption that's made here is that there's only one local minimum in this interval. So you can't have something like this. Okay, so here all these points are local optima, and you also can't have something like, say, for something like something of this form. So where these both are local optima. Okay, so as I said, so you search in this region progressively until this interval becomes very small, or you have found a point with the gradient as zero, okay, or the derivative is zero. Okay, so yeah, this I'm just doing this in case you don't remember this, or if there are some people who haven't seen this. So suppose you are allowed to do n steps. So capital N steps are allowed to be done. So your first estimate of the optimum is just the midpoint, right? So you take the first a naught plus b naught by 2. Okay, now if the gradient is 0 here, you stop and you just return this is the point. This is a critical point that you found. But now if the slope is greater than 0, so this is the point xk. So this is the situation we are considering. And at this point, the slope is greater than 0. So then what should you do? You need to look at a new interval, right? So what's the new interval that you should look at?
AK to XK.
So ak to xk, right? So you next focus on this interval. And so the new bk plus 1 is just
XK.
xk. And ak plus 1 is just ak. Okay. So then you repeat with this way. Now, on the other hand, if you have the slope as less than 0, so that's something like this. Okay. So now what would you do? Which part would you focus on?
XK to BK.
This region, right? So AK plus 1 would now be XK in the next iteration, and BK plus 1 is just BK. Okay, so you keep doing this till some n iterations, and this n has to be fixed in some way beforehand. Okay, so now how do you choose the number of iterations? Okay, so that's the next point we'll consider. So is this fine for all of you? I'm just rushing through it because I think many of you have seen it already.
There's an alternative version also, right? With where we don't use the derivative, we instead just say like if the f of ak is, we compare f of ak, f of bk, and f of xk, and then we reduce the size of the interval accordingly.
Yeah, that is also, there are different variants of this method. Okay, so here, yeah, you can do different variants depending on the functions, and sometimes you don't even evaluate the gradient. You can use some kind of, some kind of approximations for the gradient. So those are different variants that you could have for this bisection method. But the essential idea is the thing of looking, reducing the intervals by half. Okay.
Yes, ma'am.
So if you haven't seen this before, or if this is fast, just let me know. Okay. Um, okay. So in this version, like now we need to decide like where to stop, how many iterations should you choose. Okay, so usually what happens is, this is a very specific condition, f dash xk equal to 0. But when you implement this, you may not exactly like this. Equal to 0 condition is not something it's not very easy to check that exact equal to, right? Because of these numerical issues. So what you do is you're okay to have some tolerance. So as long as the derivative is within this epsilon to minus epsilon range, in this range, then you're willing to accept the x you got as the local minimum. Okay, and so this epsilon can be very small, something like maybe say 10 power minus 5, something of that sort. Okay, so notice that in each iteration of bisection algorithm, you're finding the midpoint, right? So how does this interval change? The length of this interval. So this was the previous step. At the step k, this was the interval length, which was bk minus ak. Okay, so the absolute value of this. So what about this interval, the interval length at ik plus 1? So how does this
Half
change? This is half of
half of
this. Right. Okay. So turns out that if you started off with, so at every step you are going as half. Okay, the interval size is reducing. So if you initially started off with an interval of length I naught, so the next one becomes I naught by 2. Okay, then you have I naught by 2 square and so on. So that's the way it progresses. Okay, so at step n, what you're going to get is I naught by 2 power n. Okay, so now you want this to be less than epsilon. This is the interval length, and you want that to be less than epsilon. So you just try to find the n, which gives this. Okay, now that turns out to just be log of b naught minus a naught by epsilon, where this is the initial interval that you had. Okay, so that's about the bisection method, the technicalities of how to go about, with these iterations. Now, how would you fix the initial points, right? A naught, B naught. So in this case, I told you already that, okay, A naught, B naught is the range. But if you didn't know anything about the function, how would you fix these values of A naught and B naught? Right, so remember that you want something of this form, right? An a naught somewhere here, and something, the function reduces in this range, and then it also increases and up to b naught. Something of that behavior is what you want. Okay, so any thoughts? How do you know how you can compute? You can get an initial estimate for a naught and b naught.
Ma'am, if you know the gradient at A naught and B naught, then if the gradient at A naught is negative and at B naught is positive, then somewhere between A naught and B naught, it should go to 0.
Yeah,
So,
that
by that, or the vice versa, other way around.
Yeah, that's true. So that is, of course, something you can do. Check the gradient at each of the points. But with even like if you're not allowed to check the gradient at these points, okay, is there something else you can do? So whatever you said is a valid way to fix these A naught and B naught. So that's one way. Now, if you can't check the gradients, is there something you could do? Any thoughts?
Man, we can just take some random value like a naught minus some random value, anyone, like 1, and then check the value over there. If it is greater than a naught, then of course we will get the gradient, like the positive or negative direction. We can indirectly get a gradient using the values of it.
Okay, right. So, so what you're also saying is based on finding approximations of the gradient, right? You find a small region around a naught and then try to approximate the gradient there, right? So that's all those are valid ways. Now, another way to do is you just pick some 3 points, okay, and just estimate the function value. So what you wanted was something like this, right? You wanted an x1 like this. So x1, x2, x3. So it's some 3 points here where the function value at x1 is greater than x2, and at x3 you have the function value is greater than x2. Okay, so these 2 points, the function value is greater than some point in the middle. Okay, so you just randomly pick 3 points, and if you have this, you're already done. If not, another way is, you so there are different things, right, where this could fail, where this doesn't happen. So one case is this, where you picked 3 points, x1, x2, x3, but you have the functions in this way. So you only are seeing this part of the function. So this is not going to, if you pick these as your a naught, b naught, that's not going to capture the minimum point. Okay, so these kind of issues will also appear for the case where you try to find the gradients, right? If you don't have the gradients in the way that you want, like one place it's decreasing and the other place it's increasing, then there's some fix you need to do there. Okay, something of similar nature would come there too. So here, let's see, so x1, x2, x3, it's like this. Okay, the function is a decreasing function, all these points. Okay, so now what you need to do is you want something in this range, right? You want one more point, preferably something here. Okay, so now what you can do is you can repeat, you can just sample something which is to the right of x3. Okay, so you can retain x1 as your a naught. Okay, but for b naught, you fix something to the right of x3. Okay, does that make sense? Clear? Any questions? Okay.
Ma'am,
Yes, Rajneesh.
initially you said that computing this gradient is very costly. That's why we are using this normal bisection method.
Mm-hmm.
So how are we checking that f dash x is less than 0 or greater than 0 for that if we don't have the gradient?
Yeah, so the thing is, it's not about computing the gradient. So f dash x you can compute, but the thing is finding an x such that f dash x equals 0. So that is perhaps a costly operation. Okay, because you don't, costly in the sense that you don't have a closed form for many functions. So computing the gradient may be still okay, right? But when you try to solve, it's a solution to an equation, right? You're trying to find the roots of an equation, and that may not be, you may not be able to do it on pen and paper.
Okay.
So that's the setup. Okay, so is this part clear? And if this case arises, then how you would choose the B naught? You're all quiet. Tushar says yes. Okay. Okay. Bhavna's clear. Good. Siddharth says yes. Nitish, yes. Okay. Fine. So this is one case. Now, the other case, there's one more case, right? So the symmetrically opposite case. So if you sample 3 points and you got something like this, okay? So where the function is increasing on from x1, x2, x3, and all these points, the function is increasing and you have this relation. So then what you do is you need some point, you basically want this to be covered. So you pick something in this range. Okay, so you pick a point to the left of x1. So this can be, you can fix this as B naught, but your A naught, you fix something in this range. Okay, so you can keep doing this till you are satisfied, till you get case 1. Okay, so that is, that's kind of how you fix the A naught and B naught values. Okay, so when you learned the bisection method earlier, did you see this, like how you fix the A naught, B naught values? Was there some other thing that you saw, some other approaches to fix it? And if you remember what you saw earlier?
Same thing.
Same thing, okay. Okay, great. So yeah, so that's about it. So now another use of this bisection method, this idea of searching for these regions, it helps in also solving these kind of constraint optimization methods. So remember, like in the initial classes, I just talked to you about constraint optimization, where you have this function you want to optimize and subject to some other functions taking a value less than or equal to 0. Okay, so one way, now you can use this bisection method to get some iterative techniques for solving these kind of problems, even for the multivariate case where you have an n-dimensional function. So how you would do that is, this problem is just equivalent to finding the minimum value of t, such that t is an upper bound for f of x, okay, and if gix is less than 0. So this is, you want the variables are now t as well as x. Okay, you want to find a t such that f of x is less than t and gx is less than or equal to 0 for every I. So this is something you should verify that these two are actually equivalent. Okay, so yeah, so now what happens is I mean, just a quick check on why this is equivalent is, suppose this function is of this form, and suppose you fix this. Okay, so suppose you fix this as your t. Okay, and the x's are in this range. So okay, so but the thing is, you can make this t even smaller by choosing something here. Okay, so if you choose, and so this would be the x, right, the corresponding x for this t. Now if you choose something here, if this is your t, then you can get a better value. Okay, it gets minimized. So that's why these two are sort of equivalent. So now suppose you have a t, and suppose you fix some value of t, and there is some way to test whether this set is a feasible set, in the sense that you have some way to tell you that for this t, is there some x for which f of x is less than or equal to t, and gix is, this has to be less than 0. Okay, so it's a typo. So gix is less than or equal to 0. So do you have a point x which satisfies these constraints? So suppose you have this kind of a black box which tells you that, then what you can do is you can make repeated calls to that black box. So how would you do that? So first time you say that there is some x which is feasible. So it means that, something like this. Okay, there is some x for which f of x is less than or equal to t. So what you can do is you try with some lower value of t. So this is the next t you can take. Okay, a lower value of t you take. Now again you call this black box. If you found that there's again some function, again you try to lower the value of t. Okay, now at some point, suppose you don't, suppose your next point was something here. Okay, so this is the, say, the after many iterations, okay, you got this t, this t2, the one that marked here. So here now there is no x such that f of x is less than this t2. Okay, so then what you have to do is you have to again increase it. So the previous one you had was somewhere here. So maybe you take half of that. Okay, and it's kind of a grid search that you're doing here to finally converge to the minimum point. Okay, so this idea is an important one because even later, if those of you are doing the machine learning course, you will see that it gets applied in what is called this cross validation. Okay, so when many times you have some parameter which you want to somehow fix it. Okay, and you want to ensure that that is what is most important, most valuable for you, but then you don't have a way to directly do it, so you divide the whole region into sort of grids and keep reducing the size of the grid. It's like a search space. Okay, so yeah, so this is one thing about how you use bisection method in constrained optimization. So I've seen like many works, like many research papers, even now, like they have complicated constrained optimization problems and they don't know how to solve it. So this is a first method that helps them to just do a check, okay, on what the solutions would be. Okay, now there's a connection between testing for feasibility and optimization. So if you remember this black box thing that we just saw now, it's just doing a feasibility check. Okay, so there are these deep connections in the terms of complexity. So if this kind of feasibility problem is if there is an easy way to do it, then usually even the optimization problem can be done easily. Okay, so there's this huge connection between feasibility and optimization, which you'll probably see it even later on in the course. Okay. Yeah. So that's about the bisection method. Now, any questions so far? All good?
Ma'am, isn't optimization also feasibility of the right kind of constraints? Then,
Yeah, exactly. So that's why there is this connection, right? I mean, you can model an optimization problem in terms of an appropriate feasibility check, but only thing you need to combine feasibility and some sort of a search. So that's how you view one way to view optimization would be that. But the search also is something, right? Like, so this is a feasibility test, but you need to fix this value of t appropriately, right? So it's a combination of feasibility and a search, right? It's fine. Did it answer your question, Siddharth?
yes, ma'am.
Okay. Okay, so I think things are hopefully clear for all of you, for the rest of you as well. So if this is clear now, so this is one method. Now we'll just look at another method called the Newton's method. So is this something you've seen in the other course? Newton's method, Newton-Raphson or Newton method?
Yes, ma'am.
Yes, ma'am.
Yeah. Okay, fine. So then I think I can do a quick brush up. So just let me know if something is unclear, if you want to go slower or anything. So, so Newton's method is yet another way in which you can do some iterates, and it also makes use of the second order derivatives. So where the bisection method used only the first derivative information. Okay, so the idea in Newton's method is to build a quadratic approximation at any point. Okay, and then you find the minimum of this quadratic approximation, and you keep doing this. Okay, so so for any function you take, okay, when you're trying to build a quadratic approximation at any xk, what you're in essence trying to do is you want to find this function, right, g of x, which is of the form ax square plus bx plus c. And in particular, you want to find these values of a, b, and c when you're trying to construct it in such a way that g of xk, if you take the point xk, that matches with the function value itself because there's an approximation for f. And similarly, the gradients, the first two gradients also match. Okay, so it turns out that if you try to solve these values of a, b, and c based on these equations, what you're going to get is just going to be a very familiar form to you. So since you guys are familiar with it, I've just written this down. And just let me know if you want an explanation for this. So the values of a, b, and c which satisfy these equations are what is given here. So if you write this down, what you're going to get if you want to plug in here, what you're going to get is half. So a is just the second derivative. So f prime of xk times x square plus b is this one. So x times f dash xk. Okay, minus f dash xk minus xk times f double dash xk. Okay, it's going outside this. Okay, and c is just f of xk. This is just the constant term, right? Minus xk times f dash xk minus half xk square f double dash xk. Okay, so I'm just writing out the overall function based on these values of a, b, and c. So it turns out that if you do some simplifications, what you're going to get here is just the second order Taylor series approximation about xk. Okay, so this is what we have seen earlier, right? So now the idea in Newton's method is just to find some value of x, which makes this quantity, this is the second order approximation, which makes the derivative of that 0. Okay, so now the same thing, if you take the derivative of this function, so this is a constant, so it doesn't but in terms of the computation, yeah, you have this f dash xk and you have this term x minus xk times f dash xk, and that has to be 0. Okay, so yeah, so this so let me just go over that again. So this is a constant because there's no x here. Now this one, if you take the derivative, you'll get f dash xk. So that's what this is. And now this one, if you take the derivative with respect to x, you're going to get this function, x minus xk times the second derivative. So in turn, what you're going to get now, so this is going to be 0, and the x that gives you this is just going to be xk minus f dash xk by f double dash. So this is the next step that you take. Okay. So in particular, so this is giving you a critical point of g dash. Now, in particular, like if you take the second derivative, okay, so what you're going to, if you remember, g was just this. So the second derivative of g with respect to x is just 2a. So whenever a is greater than 0, if you have this, then you are going to get a minimizer of gx. So remember, that was the our necessary and sufficient conditions, right? So the second derivative of g, if it's greater than 0, what you're going to get here is the minimizer of g. Okay, so that's how you go about. So at every step, you find this new point by this iterative method. Okay, and until you have a point for which you know, I think this has to be gradient. So the gradient is less than epsilon. Okay, so that is the norm gradient is less than epsilon. That's the point of desired accuracy. Okay, so yeah. So is the algorithm fine? Any questions on the Newton method? So I'm kind of quickly rushing through it because you said that you've already seen it. So if somebody has not seen it or it's not clear, please stop me. Okay. Okay. All right. So now there are some advantages of this, and it works sometimes and sometimes it doesn't work. So it's faster than the bisection method for many cases, but sometimes you can move in the wrong directions. So that can happen, you know, in these kind of functions, for which it usually happens when the second derivative, if it is less than 0. Okay, so even for the approximation you take, if you get something of this form, then originally you started off with xk here, but by trying to find the point for which, you know, the gradient of this approximation is 0, you're moving farther. You're going to xk plus 1, which is here, whereas x star was on this side. So, you know, that these are some of the cases where Newton's method doesn't really help you out. Okay, so and similarly, you can also diverge, you know, depending on the starting point. So for example, something of this case, right, fx is cube root of x. So if you evaluate these steps, the Newton steps, what you're going to get is xk plus 1 is just minus 2 times xk. Okay, so here clearly you want a point as 0. You want to finally reach the 0 point. So where x is 0, that's where this is minimum. Okay, but yeah, so you keep going, keep swaying in either ways. So that's an example of divergence. Okay, so yeah, so I don't know if you saw the view of Newton's method in terms of an optimization, or whether you saw it in terms of the roots of an equation. What did you see earlier in the other course? Guys, am I talking to myself? The roots of polynomials. So that's what you saw. Okay.
Yes.
So what you saw is the roots. So the roots was yeah. So so this was the actually the initial way in which the Newton's method got built, the Newton-Raphson method, to find the roots of the equation. Okay, there was no optimization. So in some sense, this is actually, when you solve an optimization problem to find the critical point, you're actually finding the roots of the differential, right? You want to find a point for which f dash x is 0. Okay, so in that sense, you're trying to find the roots, and that's why it's an extension of what you would have seen in the case of solving the roots. Okay, so this is probably what you saw. So you have a function like this. You you start with at some point x naught, okay, and you take a first order approximation here, and you see where that function. So the blue one that I have here is the first order approximation at x naught, and you see where that touches 0. So that you call it as x1. Now, at this point, you see you construct another first order approximation. So that would be something like this, x2. And I mean, you see where that touches 0, and you keep doing this, right? So the idea is just similar in the case of optimization also. Okay, so the difference is, here you were going with the first order approximation, just made use of something like this. It's a linear form in X, whereas when you want to optimize, since you're looking at instead of h, you have the gradient f dash of x. So that's when you will have the second derivative of f also. So in the case of optimization, you're looking at a quadratic approximation. Okay, so yeah, so I think I will just quickly brush through this because you've already seen this, I guess. Okay, so one thing that I don't know if you've seen these other issues that could arise in the case of roots, finding the roots of an equation. So I found this content in Professor Ali Ahmadi's notes quite, it's quite insightful. So he has taken an example for which, this is a function. Okay, here the case is you want to find the roots of g of z, not minimize it. So you want to find a point z for which the z power 5 minus 1 is 0. Okay, so and you're looking at the complex plane. Okay, so turns out there are 5 roots here, right? And so this is an illustrative visual where, if your initial point x naught, depending on where you start, you're going to get a different answer. Okay, so this is a whole region of the complex plane. And if you start from here, I mean, anything in this region, which is, I don't know, which is like kind of greenish brown. So if you start from here, you will come to the same point. Okay, you will finally converge to the same point if you apply Newton's method. But whereas if you start anywhere in this green region, for all points, I mean, for all x naughts in this green region, you will reach the same point, and so on. So you can see that, even there are these minute areas as well. So if you just change by a very small area, the point that you converge to is going to be very different. Okay, so that is the kind of thing that happens sometimes in Newton's method. It's very sensitive to the initial point. Okay, and you have to be careful in choosing, the initial point. Sometimes, having some prior knowledge about the function that you're trying to optimize, that helps to choose the initial point. Okay, and perhaps you've also seen this kind of a divergence thing even in the case of finding roots. So where your initial point is x naught, and the first order approximation is something like this, you go to x1, and then you go here, and it's going farther and farther away from this point. That was where the function took a value 0. Okay, so these are some of the issues, and similar issues also arise in optimization. So that was a glimpse of it, that what you saw some time back. Okay. So that's the Newton's method. You will see later that, these ideas can also be generalized for higher order functions in the sense of, more variables. So multivariable functions also, this idea gets used. Okay. And another variant of the Newton's method is what is called the secant method. Okay, this was also used to, find the roots of an equation, but it got, adapted to the context of optimization. Okay, so here instead of finding Newton's method, you had to find the second derivative. But here, instead of, suppose you don't have access, or it's not, suppose here, you cannot compute it very easily, then what you do is you use this kind of an approximation. Okay, so this is called the method of finite differences. Okay, so where you have some previous points that are available to you. So you have x1, x2, and so on up to xk. So what you can do is the second derivative, you just approximate it with the difference of the function values f dash at xk and xk minus 1. So remember, it was you had this by definition. This is just the limit of this difference. As xk and xk minus 1 are very close by. So this is trying to just compute this numerically. And the same thing you can do with the Newton step. Instead of f dash, f double dash, now what you do is you just plug in this formula. Okay, so that is going to give you something of this form, and that simplifies. You can do these simplifications and you will get another expression of this form. So this is another iterate. So secant method is also something that people do use, but only thing is that here, instead of starting with 1 point x0, you need 2 points x0 and x1. Okay, those are the initial points, and then you can at every point you can find the new xk, okay, based on this iterate. Okay, so yeah, so I just wanted to introduce some of these one-dimensional methods to you. Basically, those are all from root finding, but it can be used for optimization. Okay, so any questions till this point? So I'm done with what I needed to cover today. Okay, so in the next class we will see some other iterative techniques, something like gradient-based approaches, gradient descent, and so on. So are there any questions? I mean, you can leave if you are done. I mean, if you have some other class, or I'll stay around for some questions if any of you have. So, right. No questions. Okay. Rajnish, it's clear. Okay. All clear. Okay. Good. Okay. So thanks everyone for being here. So have a good day, and we'll see you tomorrow at 2 p.m. Okay.